the origin of lunar volcanoes. Many theoretical efforts, some of considerable violence, have been made to reconcile the supposed physical contradiction presented by the great magnitude and area of former volcanic activity of the Moon, and the present absence of water on its surface. So long as we accept the generally received belief that water is a necessary agent in the evolution of volcanic forces, the difficulties presented by the lunar surface are rather increased than diminished by further examination and speculation. We know that lava, scoriae, dust, and other products of volcanic action on this Earth are mainly composed of mixed silicates, those of alumina and lime preponderating. When we consider that the solid crust of the Earth is chiefly composed of silicic acid and of basic oxides and carbonates which combine with silicic acid when heated, a natural necessity for such a composition of volcanic products becomes evident. If the Moon is composed of similar materials to those of the Earth, the fusion of its crust must produce similar compounds, as they are formed independently of any atmospheric or aqueous agency. This being the case, the phenomena presented by the cooling of fused masses of mixed silicates in the absence of water become very interesting. Opportunities of studying such phenomena are offered at our great ironworks, where fused masses of iron cinder, composed mainly of mixed silicates, are continually to be seen in the process of cooling under a variety of circumstances. I have watched the cooling of such masses very frequently, and have seen abundant displays of miniature volcanic phenomena, especially marked where the cooling has occurred under conditions most nearly resembling those of a gradually cooling planet or satellite. That is, when the fused cinder has been enclosed by a solid, resisting and contracting crust. The most remarkable that I have seen are those presented by the cooling of the tap cinder from puddling furnaces. This, as it flows from the furnace, is received in stout iron boxes, cinder bogies, of circular or rectangular horizontal section. The following phenomena are usually observable on the cooling of the fused cinder in a circular bogie. First, a thin, solid crust forms on the red-hot surface. This speedily cools sufficiently to blacken. If pierced by a slight thrust from an iron rod, the red-hot matter within is seen to be in a state of seething activity, and a considerable quantity exudes from the opening. If a bogie filled with fused cinder is left undisturbed, a veritable spontaneous volcanic eruption takes place through some portion, generally near the center, of the solid crust. In some cases, this eruption is sufficiently violent to eject small spurts of molten cinder to a height equal to 4 or 5 diameters of the whole mass. The crust once broken, a regular crater is rapidly formed, and miniature streams of lava continue to pour from it, sometimes slowly and regularly, occasionally with jerks and spurts due to the bursting of bubbles of gas. The accumulation of these lava streams forms a regular cone, the height of which goes on increasing. I have seen a bogie about 10 or 12 inches in diameter and 9 or 10 inches deep, thus surmounted by a cone above 5 inches high, with a base equal to the whole diameter of the bogie. These cones and craters could be but little improved by a modeler desiring to represent a typical volcano in miniature. Similar craters and cones are formed on the surface of the cinder, which is not confined by the sides of the bogie. I have seen them well displayed on the running-out beds of refinery furnaces. These, when filled, form a small lake of molten iron covered with a layer of cinder. This cinder first skins over, as in the bogies, then small crevasses form in this crust, and through these the fused cinder oozes from below. The outflow of this chasm soon becomes localized, so as to form a single crater, or a small chain of craters. These gradually develop into cones by the accumulation of outflowing lava, so that when the whole mass has solidified, it is covered more or less thickly with a number of such hillocks. These, however, are much smaller than in the former case, reaching to only 1 or 2 inches in height, with a proportionate base. It is evident that the dimensions of these miniature volcanoes are determined mainly by the depth of the molten matter from which they are formed. In the case of the bogies, they are exaggerated by the overpowering resistance of the solid iron bottom and sides, which force all the exudation in the one direction of least resistance, viz. Toward the center of the thin upper crust, and thus a single crater and a single cone of the large relative dimensions above described are commonly formed. The magnitude and perfection of these miniature volcanoes vary considerably with the quality of the pig iron and the treatment it has received, and the difference appears to depend upon the evolution of gases, such as carbonic oxide, volatile chlorides, fluorides, etc. I mention the fluorides particularly, having been recently engaged in making some experiments on Mr. Henderson's process for refining pig iron, by exposing it when fused to the action of a mixture of fluoride of calcium and oxides of iron, alumina, manganese, etc. The cinder separated from this iron displayed the phenomena above described very remarkably, and jets of yellowish flame were thrown up from the craters while the lava was flowing. The flame was succeeded by dense white vapors as the temperature of the cinder lowered, and a deposit of snow-like flocculent crystals was left upon and around the mouth or crater of each cone. The miniature representation of cosmical eruptions was thus rendered still more striking, even to the white deposit of the haloid salts which Palmieri has described as remaining after the recent eruption of Vesuvius. The gases thus evolved have not yet been analytically examined, and the details of the powerful reactions displayed in this process still demand further study, but there can be no doubt that the combination of silicic acid with the base of the fluor spar is the fundamental reaction to which the evolution of the volatile fluorides, etc., is mainly due. A corresponding evolution of gases takes place in cosmical volcanic action whenever silicic acid is fused in contact with limestone or other carbonate, and a still closer analogy is presented by the fusion of silicates in contact with chlorides and oxides, in the absence of water. If the composition of the moon is similar to that of the Earth, chlorides of sodium, etc., must form an important part of its solid crust. They should correspond in quantity to the great deposit of such salts that would be left behind if the ocean of the Earth were evaporated to dryness. The only assumptions demanded in applying these facts to the explanation of the surface configuration of the moon are first, that our satellite resembles its primary in chemical composition, second, that it is cooled down from a state of fusion, and third, that the magnitude of the eruptions due to such fusion and cooling must bear some relation to the quantity of matter in action. The first and second are so commonly made and understood that I need not here repeat the well-known arguments upon which they are supported, but may remark that the facts above described afford new and weighty evidence in their favor. If the correspondence between the form of a freely suspended and rotating drop of liquid and that of a planet or satellite is accepted as evidence of the exertion of the same forces of cohesion, etc., on both, the correspondence between the configuration of the lunar surface and that of small quantities of fused and freely cooled earth crust matter should at least afford material support to the otherwise indicated inference, that the materials of the moon's crust are similar to those of the Earth's, and that they have been cooled from a state of fusion. I think I may safely generalize to the extent of saying that no considerable mass of fused earthy silicates can cool down under circumstances of free radiation without first forming a heated solid crust, which, by further radiation, cooling, and contraction, will assume a surface configuration resembling more or less closely that of the moon. Evidence of this is afforded by a survey of the spoil banks of blast furnaces, where thousands of blocks of cinder are heaped together, all of which will be found to have their upper surfaces that were freely exposed when cooling, corrugated with radiating miniature lava streams that have flowed from one or more craters or openings that have been formed in the manner above described. The third assumption will, I think, be at once admitted, inasmuch as I think it is but the expression of a physical necessity. According to this, the Earth, if it is cooled as the moon is supposed to have done, should have displayed corresponding irregularities, and generally the magnitude of mountains of solidified planets and satellites should be on a scale proportionate to their whole mass. In comparing the mountains of the Moon and Mercury with those of the Earth, a large error is commonly made by taking the customary measurements of terrestrial mountain heights from the sea level, as those portions of the Earth which rise above the waters are but its upper mountain slopes, and the ocean bottom forms its lower plains and valleys. We must add the greatest ocean depths to our customary measurements in order to state the full height of what remains of the original mountains of the Earth. As all the stratified rocks have been formed by the wearing down of the original upper slopes and summits, we cannot expect to be able to recognize the original skeleton form of our water-washed globe. If my calculation of the atmosphere of Mercury is correct, viz., that its pressure is equal to about 1/7 of the Earth's, or 4¼ inches of mercury, there can be no liquid water on that planet, excepting perhaps over a small amount of circumpolar area, and during the extremes of its aphelion winter. Thus the irregularities of the terminator indicating mountain elevations calculated to reach to 1/253rd of the diameter of the planet are quite in accordance with the above stated theoretical consideration. There is one peculiar feature presented by the cones of the cooling cinder, which is especially interesting. The flow of fused cinder from the little crater is at first copious and continuous. Then it diminishes and becomes alternating by a rising and falling of the fused mass within the cone. Ultimately the flow ceases, and then the inner liquid sinks more or less below the level of the orifice. In some cases where much gas is evolved, this sinking is so considerable as to leave the cone as a mere hollow shell, the inner liquid having settled down and solidified with a flat or slightly rounded surface at about the level of the base of the cone, or even lower. These hollow cones were remarkably displayed in some of the cinder of the Henderson iron, and their formation was obviously promoted by the abundant evolution of gas. If such hollow cones were formed by the cooling of a mass like that of the Moon, they would ultimately and gradually subside by their own weight. But how would they yield? Obviously by a gradual hinge-like bending at the base towards the axis of the cone. This would occur with or without fracture, according to the degree of viscosity of the crust and the amount of inclination. But the sides of the hollow cone shell, in falling towards the axis, would be crushing into smaller circumferences. What would result from this? I think it must be the formation of fissures, extending for the most part radially from the crater towards the base, and a crumpling up of the shell of the cone by foldings in the same direction. Am I venturing too far in suggesting that in this manner may have been formed the mysterious rays and rills that extend so abundantly from several of the lunar craters? The upturned edges or walls of the broken crust, and the chasms necessarily gaping between them, appear to satisfy the peculiar phenomena of reflection which these rays present. These edges of the fractured crust would lean towards each other and form angular chasms, while the foldings of the crust itself would form long concave troughs extending radially from the crater. These, when illuminated by rays falling upon them in the direction of the line of vision, must reflect more light towards the spectator than does the general convex lunar surface, and thus they become especially visible at the full moon. Such foldings and fractures would occur after the subsidence and solidification of the lava-forming liquid, that is, when the formation of new craters had ceased in any given region. Hence, they would extend across the minor lateral craters formed by outbursts from the sides of the main cone, in the manner actually observed. The fact that the bottoms of the great walled craters of the Moon are generally lower than the surrounding plains must not be forgotten in connection with this explanation. I will not venture further with the speculations suggested by the above described resemblances, as my knowledge of the details of the telescopic appearances of the Moon is but second-hand. I have little doubt, however, that observers who have the privilege of direct familiarity with such details will find that the phenomena presented by the cooling of iron cinder or other fused silicates are worthy of further and more careful study.